Rethinking the Origins of the Universe, a New Theory. The very origins of the universe are under debate again. Could quantum gravity reshape our understanding of the Big Bang? A revolutionary cosmological framework proposed by researchers at the Universities of Padua, Barcelona, and Pisa challenges the long-held assumption that inflation, that explosive expansion moment post-Big Bang, is the key to explaining cosmic uniformity. Instead, they're suggesting a universe shaped by quantum gravitational waves rather than mysterious inflaton fields. Groundbreaking theory reimagining the universe's genesis. Imagine a universe born not from mysterious, unobservable forces, but from the natural interplay of gravity and quantum mechanics. This is the bold proposition put forward by a team of scientists led by Raúl Jiménez, an ICREA researcher at the Institute of Cosmos Sciences, ICCUB, at the University of Barcelona, in collaboration with the University of Padua, Italy. Their study, recently published in Physical Review Research, challenges long-standing assumptions about the origins of the cosmos, and it's sparking conversations that could reshape our understanding of reality itself. But here's where it gets controversial. What if everything we thought we knew about the first moments of the universe was based on shaky ground? For decades, physicists have relied on the inflationary paradigm to explain how the universe expanded exponentially within a fraction of a second after the Big Bang. While this model has been instrumental in shaping modern cosmology, it comes with a significant flaw. It depends heavily on adjustable parameters, commonly referred to as free parameters. These are essentially dials that scientists can tweak to fit their models to observed data. The problem? Too many free parameters make it hard to distinguish between genuine predictions and mathematical fine-tuning. Enter the groundbreaking alternative proposed by Jiménez and his colleagues. Their model eliminates the need for these speculative adjustments altogether. Instead, they suggest that the early universe began in a state described by de Sitter space, a well-established concept in theoretical physics that aligns with current observations of dark energy. By grounding their theory in observable phenomena rather than hypothetical constructs, the researchers aim to provide a more robust framework for understanding the universe's infancy. And this is the part most people miss. The new model doesn't rely on exotic particles or fields to explain cosmic structure formation. Instead, it points to something far simpler: gravitational waves. These ripples in spacetime, predicted by Einstein's theory of general relativity and later confirmed through experiments like LIGO, take center stage in the Keam's proposal. According to their findings, spontaneous quantum fluctuations in spacetime during the universe's earliest moments created tiny density variations. Over time, these variations grew nonlinearly, interacting and amplifying one another to form the galaxies, stars, and planets we observe today. For years, we've been trying to piece together the puzzle of the universe's beginnings, using tools built on things we've never actually seen, explains Raúl Jiménez. What makes this approach so exciting is its simplicity. We aren't inventing new components. We're showing that gravity and quantum mechanics alone might be enough to tell the full story. This perspective shifts the focus away from speculative elements toward a deeper exploration of fundamental physics principles. If proven correct, this theory could herald a new era in cosmology. It would mean that humanity doesn't need to invoke unobservable inflatons or other hypothetical entities to describe the cosmos. Instead, the secrets of the universe may lie within the intricate dance of gravity and quantum effects, a revelation that bridges two of science's most profound disciplines. Of course, not everyone will agree with this interpretation. Some might argue that removing inflation entirely oversimplifies the complexities of the early universe. Others may question whether gravitational waves alone can account for all observed structures. So let's open the floor. Do you think this new model represents a leap forward in our understanding of the cosmos? Or does it raise more questions than answers? Share your thoughts in the comments below. We'd love to hear your take. For those interested in diving deeper into the technical details, the research paper titled Inflation Without an Inflaton by Bertacca, D. et al. Was published in Physical Review Research in 2025. You can access it via DOI 10.1103/VFNY-PGC2. Beyond Big Bang, gravity quantum physics reveal universe's surprising origin. What if the universe didn't start with a colossal explosion, but emerged quietly from a stable, expanding void? This bold idea is shaking the foundations of cosmology, challenging the widely accepted Big Bang theory. A groundbreaking study from the Universities of Barcelona and Padua proposes that the universe's birth wasn't a fiery event, but a serene process driven by gravity and quantum mechanics alone. But here's where it gets controversial. This theory ditches the need for speculative elements like the inflaton field, offering a cleaner, more testable explanation for how cosmic structures formed. Could this be the scientific revolution we've been waiting for? Synopsis. Researchers from the University of Barcelona and the University of Padua have unveiled a theory that could rewrite our understanding of the cosmos. Instead of relying on the rapid inflationary expansion of the Big Bang, they suggest the universe began in a stable de Sitter space, a smooth, empty expanse driven by dark energy. In this model, tiny quantum fluctuations, like ripples in the fabric of spacetime, evolved into gravitational waves, creating the density differences that allowed galaxies, stars, and planets to form. This approach not only simplifies the narrative, but also grounds it in well-established physics, making it a compelling alternative to the Big Bang's more speculative aspects. The problem with inflation. For decades, the inflation theory has been a cornerstone of cosmology, explaining the universe's uniformity and structure. However, it hinges on hypothetical particles and forces that have never been observed. This new theory eliminates those uncertainties, relying solely on gravity and quantum mechanics, two pillars of modern physics. If proven correct, it could mark a paradigm shift in how we study the universe's origins. How did the universe begin then? Imagine a universe starting not with a bang, but with a whisper. The researchers propose that the early universe was a de Sitter space, a theoretical model where space expands due to dark energy, devoid of matter or light. In this setting, quantum fluctuations naturally occurred, eventually transforming into gravitational waves. These waves created the tiny variations in density that allowed matter to clump together, forming the cosmic structures we see today. And this is the part most people miss. This process doesn't require any unseen forces or particles, making it both elegant and verifiable. What is de Sitter space? De Sitter space is a theoretical concept describing a universe dominated by dark energy, where space expands endlessly without matter or light. Scientists use it to study how the universe behaves under the influence of dark energy, particularly in its earliest or farthest future stages. This theory leverages de Sitter space to explain the universe's birth in a way that aligns with our current understanding of dark energy. Big Bang or de Sitter space, what's the difference? This theory doesn't reject the Big Bang outright, but offers a different perspective. Instead of a violent explosion, it suggests the universe emerged from a stable, expanding de Sitter space. While the Big Bang relies on speculative elements like the inflaton field, this model uses only gravity and quantum mechanics to explain cosmic origins. It's a minimalist approach that invites new ways to explore the universe's earliest moments. What does this mean for science? The beauty of this theory lies in its testability. Unlike inflation, which depends on unobserved phenomena, this model makes predictions based on real, observable physics. Future studies of gravitational waves and cosmic structures could either validate or debunk it. Lead author Raúl Jiménez describes the theory as simple, elegant, and powerful, emphasizing its reliance on established physics rather than inventing new elements to fit the math. If confirmed, it could revolutionize our understanding of the cosmos. A controversial question. Here's a thought. If this theory holds up, does it mean the Big Bang was just a convenient placeholder for something far simpler? Could we be on the brink of a scientific breakthrough that reshapes everything we thought we knew about the universe's beginnings? Let's spark a discussion. Do you think this theory could replace the Big Bang, or is there still room for both ideas? Share your thoughts in the comments below.